Hi. So last time we stopped here, we saw that we had no resistors in series anymore, so we can't combine anything in series. Then the next question was, okay, are there any two resistors in parallel? So we need to have a way, a trick to be able to tell easily if two resistors are in parallel. And well, first of all, what is special about having two resistors or any two circuit elements in parallel? What's special is that two resistors are in parallel if the voltage, which is the potential difference, the difference of potential across them is the same. This is the essential property of two elements that are in parallel. They have the same voltage across them. Now, how do we tell if two things are in parallel? Well, two resistors are in parallel if it's possible to draw a closed loop in the circuit which contains only those two resistors along the loop and no other elements. Now, I insist that when I say that, I say they contain, the loop must contain only those two resistors. It's along the loop, along the edge of the loop. I'm not saying inside the loop, but along the loop. You must have no other elements, so no other resistor, no battery, nothing else. But it's perfectly okay if the loop contains junctions. So let's apply this. Okay, for example here, is it possible to draw a loop that contains only two resistors along the loop? Just to show you what I mean, if you look at this loop here, you draw a closed loop. I'm always talking about loops. You draw this closed loop and you see that along the loop I have only R2 and R4. So R2 and R4 are in parallel. Notice that R3 is inside the loop, but I don't care about that. I'm just talking about along the loop. So along the loop there's only R2 and R4, therefore they are in parallel. Of course, they're not the only thing, only uh, resistors in parallel in this example. For example, you can draw this closed loop here, and you see that R2 and R3 are in parallel. Again, along the loop, it's perfectly okay now to have junctions. It's very different from the rule for series. In series, you must be able to go from one resistor to the other resistor without going through a junction, but it's okay to go through another circuit element. But here it's the opposite. It's okay to have a junction along the loop, but I must have no other circuit element. So no battery and no third resistor. So R2 and R3 are in parallel. You can also, then it's obvious that R3 and R4 are also in parallel. So you see 2 and 3 are in parallel, 3 and 4 in parallel, 2 and 4 in parallel. So those three resistors are all in parallel with one another. We can combine all of them in one step using the law for parallel combinations. Now, just to show you two resistors that are not in parallel, if you draw this loop, you go here, and you close the loop by going this way. Now, R2 and R15, R2 is here, R15 is here. They're both along the loop, but there's something else in the loop. Along the loop is the battery here. So because there's another circuit element, R2 and R15 are not in parallel. Okay, so now that's the trick. That's the way to tell if two things are in parallel. So 2, 3, and 4 are all in parallel with one another. So we have this result. Okay. Now that we know that, we can we could combine 2 and 3, and then the resulting resistor we could combine with R4, or we can combine all three of them in one step. This is what we'll do. So I replace R2, R3, and R4 by their equivalent resistance. I call that R2, 3, 4. And using the law for resistors in parallel, I get this. Okay. Now I have to redraw the circuit. So I want to replace 2, 3, and 4 by their equivalent resistance. But how do I redraw the circuit in case like this? So how do we simplify the circuit? The rule in parallel is this. You replaced one of the resistors in parallel by R equivalent, which is 2.847 ohms here. You replaced one of them. It doesn't matter which one. You could replace the R2 or replace R3 or R4, it doesn't matter. You replace one of them. What do we do with the others? For the others, you remove completely the branches that contain the other resistors. So if we do that in our case, well, remember what we had before. Okay, that was our R2 here. The circuit we had before was this. We had, I think it was R3 here that was like this, and we had R4 here like this. So what we did is that I chose to replace R2 by R equivalent here. I could have as well replaced this one by R equivalent or this one by R equivalent, doesn't matter. So I chose to replace this one by R equivalent, and the branch that contains this one and the branch that contains this one, I've removed completely. So if you remove this branch and you remove this branch here, you're left with this. Now, there's this strange situation here where we have this wire here that stops nowhere. Now, in terms of a circuit, if there is nowhere here for the current to flow, there would be no current anywhere in this segment of wire here. So there's no current at all here. So in terms of solving the circuit, this piece here you can completely forget and just remove completely. Forget about this piece here. So we end up with this very simple circuit with only one loop. Like this to the resistor here, like this, and back here. There's only one loop. Then it's easy. We're basically done. Now it's clear this one, R234 and R15 are in series now. They're in the same branch. There's only one branch here. So we can combine them. If you combine them, you just get 14 plus 2.847. So you get 16.847. By the way, I'm keeping 4 sig figs in the steps here because I want to have more precision. At the very end, I'll go back and round off everything to 3 sig figs. So we replace R234 and R15 by, I call that R12345. That's the combination of all the resistors, which has a value of 16.847 ohms. Okay. Now that we have the final R equivalent, we can find the current in this branch, which is, by the way, flowing this way, right? It's flowing away from the positive terminal like this here. So it's flowing in the counterclockwise direction. The current is 12 volts divided by R equivalent, 0.7123 amps. Okay, this is the current that flows out of the battery. So that means that in the original circuit, that will also be the current flowing out of the 12-volt battery. Okay? Now, I have to undo my steps now. Well, remember R15, that came from this 14 ohms, came from R1 and R5 in series. So if you know the current in R15, which is just this 0.7123 amps, the current flowing in R15 will also be the current flowing in R1 and R5 because they were in series. But if you look at this resistor here, it came from combining 3 resistors in parallel. Now, the connection when you do your steps is that the resistor here, because it came from 3 resistors in parallel, you have to remember that when you have things in parallel, what is common to all of them is their voltage, the difference of potential across them. So in order to undo my step, I have to find the delta V here, because this delta V would be the same as the delta V across R2, R3, and R4. So how do I find the delta V here? I just use Ohm's law. Delta V across R234 is just R234 times the current flowing through it, which is just the 0.7123 amps. So I know the current, I know R234, I multiply, I get that, 2.028 volts. This is the voltage across this resistor, which is also the voltage across R2, R3, and R4, because they are all in parallel. So I go back here. Then I undo my step. I go back. I undo my step of those 3 resistors that were combined in parallel. Now I know the voltage here is 2.028 volts. The voltage here is 2.028 volts. Voltage here is also that. So now I can find I have the voltage across those three resistors, and then I can find the current through each of them. I just use Ohm's law. So for I2 here, I just use delta V over R2. So 2.028 volts divided by 7 ohms, that gives me this current here, I2. And then I repeat for 2.028 volts divided by 12 ohms here to find I3, and then I find I4 also. So I know the currents in all the resistors now. Okay, so I go back to the very first circuit, the original circuit. Now I have R1 and R5. R1 and R5 have the same current as the current flowing out of the battery, which was this 0.7123 amps. And we know the currents in R2, R3, and R4. Okay, so we know the currents everywhere. The current in I2, R2, R3, R4, and the current in R1, R5 are both equal to the current flowing out of the battery. Okay. Now we look at the directions. In this branch here, the branch that contains the battery, is obvious. The current flows away from the positive terminal. So I know the current here is going this way, and this current is this 0.7123 amps. It goes this way. The current goes here, and it will split. Now, the current going here has to go this way. The reason I know that is that I know that you see well this current here goes this way. I know that this point here is at higher potential than this point here, right? From between here and here, we know the voltage was 2.028 volts, and we know that the current is, if you replace all of those here by R equivalent, you know that this point is at higher potential than this point, because the current in R equivalent goes that way. So I know the current here goes this way, and it has the value I4 given here. Now, notice the point here is at higher potential than the point here. That's why the current flows this way. But this point is at the same potential as this point here, and this point here is at the same potential as the point here. Sorry, the point here. So if this point is at higher potential than here, this point is at higher potential than here. Therefore, the current here has to go this way also. Then you apply the same reasoning. This point here is at higher potential than this point. Therefore, the current there has to flow this way. So we know I2, I3, I4, and we know their directions. Okay, now to find the currents here and here, we can just apply conservation of current at the nodes. So let's say you pick this point here, this junction here, this node. You know that from the left, there's a current of 0.7123 amps coming in, right? You know that here there's a current of I4, 0.2535 amps flowing this way. So you have 0.7123 amps here entering, only 0.2535 going out here. So there must be some current left here, which is just given by the difference of the two values. So if you do that, you just do 0.7123 amps here minus 0.2535 amps, you get this value here, which is the current coming out here. You can check your answer, because here at this junction, the current coming in must be equal to the current coming out. So this number here better be equal to the sum of I3 and I2. So if you add I2 and I3, you better get back 0.4588 amps. And within the sig figs that we're working with, it does work. Okay, so we know the current here, and we can check at the two junctions here that it is the correct value. Then finally, we are just missing one current, which is the current here. Again, you can apply this junction here. Well, you know now that there's a current coming from the left and coming here. So the current here has to go up. And what must be the value of the current going up? It must be equal to I3 plus I4. So you take I3 and I4, you add them up, and that will give you the current flowing up. And it gives 0.4225 amps. Again, you can go back here at the junction and verify that the sum of this value here, which is I2, and this current here must be equal to the current going there, which is just the 0.7123 amps. So indeed, if you check, you take I2 here and you add, I2 here, you add it to 0.4225, you would get 0.7123 amps, or no, you might have a different last digit, but within 3-sig phase, it would be equal. So that's it. We have the currents everywhere in this circuit, and we can check at all the junctions that everything is working. Okay, so we've solved the circuit. Now, as a double check, we can check that the energy is conserved, which means that when there's only one battery in the circuit, the power produced by the battery must be equal to the sum of the powers in the resistors, because the battery is given energy to giving energy to the charges, and the charges lose their energy in the resistors. And we can use any of those three equations. For battery, you must use this. For resistor, you can use either this one or this one or this one. And if you apply that to our circuit, the power of the battery, you just take 12 volts times the current in the battery, you'll find this, which if I round off to 3-sig figs is 8.55 watts. Then if you look at the powers in the 5 resistors, you add them up. Here are the values, and I get this for the sum. If I round off, I get 8.55 amps. The fact that you get this is equal to this here, the power in the batteries, is a very, very strong double check of our currents. So it's almost certain that we didn't make any mistakes for the currents. Okay, so that's how we check conservation of energy. So we've solved the circuit completely now, and we've checked our answer by checking that at the junctions, the sum of the currents coming in equal to sum of the currents coming out, and we've checked conservation of energy. So finally, our final answer is this with all the directions shown, and I give the currents with 3-sig phase, and that's the final complete answer to the solving the circuit. Thank you.